Welcome Professor Avignone, which will talk about the present and future of neutrinoless double beta decay experiment.
High technology. Okay. I have my clock here. Okay, I don't know, the audience is very varied, so I don't know what people know about this subject. But it's been a subject that's been around since the 1930s, and it's interesting. This young lady who won a Nobel Prize in '48 for her work on shell model of the nucleus actually calculated, she was the first one to calculate something where you would have a weak interaction that would jump two atomic numbers because it was locked by the pairing forces in nuclei, energetically locked from a first step. And I want you to just notice this. We can talk about it a little bit later, the accuracy of where this energy, the total energy would be. So this is something we can come back and look at how we measured this at Florida State. Because if you have do neutrinoless double beta decay, as we'll discuss, you're going to have a single energy. Okay, this is ordinary 2-neutrino double beta decay. It violates no lepton number violation. It violates no conservation laws. It's been seen in a half a dozen nuclei many times and accurately measured. This, however, is the neutrinoless double beta decay that would occur for the exchange of a light neutrino. And so, but that neutrino would have to have mass, and it would also have to be a Majorana particle, which is, of course, of interest to cosmologists. So what do we learn from it? It's the only practical way to determine if neutrinos are Majorana particles. And of course this could, if they aren't Majorana particles, leptogenesis would be, of course, one possibility for the explanation of particle over antiparticle that we see in our universe today. Measurement of the lifetime, if you could measure the lifetime, you could, using that data, along with neutrino oscillation data, you could determine the masses of all of the mass eigenstates, of the three mass eigenstates rather accurately, depending on the nuclear structure accuracy. The observation of this decay would also violate lepton number, and that's of interest to elementary particle theory. So the ancient history was that Maria Maya in 1935, she was the one that asked the question about could something like tellurium-130, by the way, that's what we're using today, one of the isotopes we are using, could it actually decay that way and jump two atomic numbers, maintaining the same atomic mass? And then, of course, a couple of years later, Ettore Majorana came up with his theory that neutrinos could be their own antiparticles, different anti-neutrino, different, being different only by its helicity. And in 1939, Wendell Furry said you could test the Majorana theory, perhaps with the neutrinoless double beta decay. Okay, so very recently we've had a nice Nobel Prize in neutrino physics, and one of my good friends, Art McDonald, won it. I will see both of these gentlemen. There's a little bit of a problem with my talk. I can't give the very latest results. That people are hiding them because at the end of this month in Sudbury, Canada, there's going to be the TAUP meeting. And the TAUP meeting is where all of the experimentalists want to show their new results. So they're not going to give them to me to show to you today. But anyway, this you'll know more. You can get online and see the very latest, because everybody's hiding their neutrinoless double beta decay data until they can show that at the top results and beat on their chests. There have been some results, but of course, you know, with half-lives on the order of 26, 27, 28, 10 to the 28 years, a few decades doesn't mean much. Okay, so the neutrinoless double beta decay really depends, what we know about it and how we predict how we should build experiments depends an awful lot on the people that have done neutrino oscillation experiments at the solar neutrinos, starting with Ray Davis and then ending up with Art McDonald and his snow army, atmospheric neutrinos, Kajita and his army in Japan, and accelerated by many different experiments. They have determined that the neutrinos most likely have 3 eigenstates. They could be in this direction, where the atmospheric neutrinos, which would also be accelerator, would have a splitting of the squares of the mass eigenstates that would have about this splitting, and the solar neutrino with about this splitting, which was rather accurately settled by the Snow experiment after several other solar neutrino experiments. Or it could have an inverted hierarchy scenario like this, where we do not know anything here, except for the cosmology gives us a limit about the sum of these neutrino, the 3 types of neutrinos. So there are bounds here that cosmology tells us we're not going to have lots and lots of electron volts of mass as for the lightest eigenstate. Okay, so our usual and our current idea is that neutrinos have 3 mass eigenstates, and they're connected to flavor eigenstates by this transformation. And this is just a rotation in a three-dimensional space, and then we end up with something just like an ordinary rotation matrix. And this is the cosine of the angle of the rotation about axis 3. This is the one about axis 2, and so forth. And this is a rather familiar thing, with one exception, that these CP violating phases are the same ones in quark physics. And we don't know what they are very well.
You mean analogous to?
Pardon?
You mean analogous to the decay phase?
Yes, okay, analogous. But we don't know what they are, Jose. Okay, so, but anyway, there have been a lot of different analyses, some recent ones have actually given us numbers with these, and I have not put the phases in here. So without the CP phases. But I wasn't talking about the Majorana phases. They have yet to go in there. And they are totally unknown. So these angles have been worked out for us from the analysis of neutrino oscillation experiments. So with these numbers, an experimentalist like myself can at least get an estimate of what kind of activity, what kind of rates one might expect for neutrinoless double beta decay if you knew something about the matrix elements. All right, so you would predict this, that the rate, the inverse of the half-life, would go by one factor would be a phase space factor. This is electron physics. This is when the electron comes out of the nucleus. The quantum mechanics has some partial reflection. That's been known since Fermi's day. This is a nuclear matrix element, a Fermi-type matrix element, and a Gamow-Teller-type matrix element. These have to be calculated with nuclear models, shell model, all these kinds of other models, which I will mention in a few minutes. The electron mass, and this is something called the effective Majorana mass of the electron neutrino. And it is defined this way, and it is calculated now with these matrix elements from the matrix we showed before, and it has one extra one new phase, which is another one completely unknown. It's the Majorana phase. It only occurs where you have Majorana particles, so it does occur in neutrinoless double beta decay. So, we put in what these are from the previous page. It's only the top matrix, the top of the matrix. This is M3, which in the inverted hierarchy could be 0, so let's let it be 0 and get the most conservative estimate. And this is the atmospheric neutrino difference in the eigenstate masses squared. And this is the solar neutrino, very small. So this one is very much smaller than that one. That one is 0, and you can make a quick estimate about the range that you would see. And with a little bit of algebra, by using the relationship between M1, M2, and M3, you can quickly come up with something like this. Unfortunately, I will choose the most optimistic will be the positive sign here. So it could be as large, where M3 is 0, it could be as large as 53 milli-electron volts. So where does that fit us? Where does that fit? Well, if we plot this effective Majorana mass of the electron neutrino against the lightest mass eigenstate, we get these plots. This would be the normal hierarchy. Can actually go to 0 with these phases. The inverted hierarchy, this is where, if I picked here the most optimistic, that would be this, but if I picked less optimistic, plus added the uncertainty with the phases, it could be as small as less than 2 times 10 to the minus 2 electron volts. The experiments to date, that is, except for those that are going to be given at the end of the month, and I'm not sure how much they would be improved. Nobody's talking to me about that. They knew I was coming here, so they won't even answer my emails. The Gerda and HDM, Heidelberg, Moscow. This is not the one with the claim, I think, but this is the one that was 1.9 10 to the 25-year bound. This was my experiment. The IJEX. They mixed those together, and this is the best you can get. Actually, they're below that now. They've got a new result, which would be announced at the end of the month. Giorgio Gratta's EXO, the large xenon experiment, which we'll discuss, is down to here, and tellurium with the Quarte and Quarticino and Quarte Zero experiment is here. Reaching down, Quarte is one of them. They're all going to reach the top here. Then you've got to make some improvements. We've been told by the agencies we've got to reach the bottom here. We've got to reach all the way through the inverted hierarchy sensitivity. Frequently we get asked, what about the possibility of the exchange of heavier particles, not ordinary light neutrinos? It could be something like a Higgs triplet, something off the standard model, or something like a SUSY particle. And this is, of course, what would you learn? Well, sitting in the audience today is a gentleman that has told us what to learn, Jose Valle, and Schechter and Valle came up with something called the black box theorem. And it says, and it's proven in this article right here, that all decay modes that engender zero neutrino double beta decay require that neutrinos involved are Majorana particles. So, maybe we don't get to measure the mass of the neutrinos, but we do know that we have Majorana particles, we do know that we have violated lepton conservation, and we do know, and we don't know, we're not able to directly measure the mass. Jose is here, and he will answer all questions that have to do with this diagram. I'm not going to do it. But anyway, that was something that, now, I'll tell you a little story. I gave a talk at the University of Texas at Austin, and I got a note in my hand, handed to me by a graduate student, that Steve Weinberg wanted to see me in his office, that he would not be at you go there, you give a talk, you have to give him an outline in his office. So I did that, and I asked him about this. This is before, without mentioning this is actually about the same time that they came up with the theory. And I asked him about the question of exchange of a heavy mayon, or a heavy particle. And he thought for a minute, and then he said, let me tell you, I wouldn't worry about it. And I never could get anything else from him about that. But apparently you also had this experience. Okay, so there are a number of candidates, good candidates. A good candidate is one where the pairing forces in the nucleus make the even-odd nuclei, or the even nuclei, much more tightly bound than the even odds between it. And so there's no possibility for a single weak interaction like a beta decay or electron capture decay. And of course that would wipe out any possibility of seeing a double beta decay. So these are a handful of good candidates. And this is something called the figure of merit, which is the phase space times the nuclear matrix element squared, and it comes out in years to the -1. And you say, well, let's make these calculations, and these uncertainties have to do, actually I think they're too small, but they have to do with the uncertainties in the nuclear models. Well, you'd say, well, neodymium is a great one. Let's do that one because it's much better than, let's say, it's an order of magnitude better than let's say, tellurium-130. Well, there are other considerations like how do you make a detector? And with neodymium, it's almost impossible. You can't isotopically enrich it very, very well because the chemistry is tough. Xenon is trivial to isotopically enrich because it's already a gas. You can put it in a centrifuge. The Russians do it by the ton. Molybdenum-100 is possible to do. You can make a tetrafluoride gas, and you can do that separation. Selenium, germanium are the same. Calcium is almost impossible to do. It only has a very tiny natural isotope of calcium-48. So it would be very expensive, and there's no chemistry to do it. So the popular ones are germanium-76, selenium-82, which, by the way, Mike Moe saw the 2-neutrino double beta decay in the lab the first time using selenium-82 in a time projection chamber. Molybdenum is good. The NAMO has done a great deal with molybdenum. And cadmium-116 can be done. Tellurium-130, it makes a very nice bolometer. We'll talk about that. Okay, so nuclear structure models, the interacting boson model, it's based on the fact that the fermions couple to make bosons, and it's not a quantum mechanical detailed model. Renormalizable quasi-particle random phase approximation is another one such model, and this is another type of QRPA model. Some of my best theoretical friends will tell me that the shell model is the most reliable. Now, what can be done here is, supposing we assume that the effective mass of the electron neutrino is 50 millielectron volts, then this was a half-life that you would have to achieve in order to see this. So if Corday, for example, you'd have to come and see something little less than 10 to the 26 years. Germanium, you would have to see something better than 10 to the 27 years. And these different models, the shell model for germanium would tell you you'd have to see about 2.5 times 10 to the 27 years. So the lower you are, the better you are. But yet again, why throw this idea away when germanium is a technology that's used everywhere, and it's very well developed technology with the highest resolution, energy resolution of any of the technologies. But you see, there's not a great deal of difference. It's not orders of magnitude. Okay, so again, I repeat this, but then I'll just use the Planck mission, there are certainly others. This cosmology pretty well tells us we probably won't have the lowest eigenstate this large. Okay, so there's so many efforts, so many experiments going on that we can't possibly look at all of these. So I'm going to look at the ones like Gerda and Majorana in germanium and Snow Plus, which is really just being built, but it has a great deal of effort going on. Super Nemo, which is another a chamber, tracking chamber. EXO 200, which has given us one of the best results, and also the Japanese experiment with xenon similar to this one, with xenon in a scintillator, and Quarte, which is operating now, and it is a cryogenic experiment. Which is okay. Start with ionization detectors, which would be Gerda, Majorana, Legend. These two germanium experiments are going to join together to make Legend, and that would be first operated in the Gran Sasso. The scintillation detector, Snow Plus, where the large scintillator, which has xenon 136 absorbed in it. Camland Zen, also the same thing, but it's in Japan. Time projection chambers, EXO, this is Giorgio Gratta at Stanford's thing. And next is a small experiment, which is just being started. It's a gas experiment in xenon in the Canfranc in Spain. Tracking chambers, Super Nemo, which is really not built yet, but it's on its way. And the cryogenic bolometry, Quarticino, Quarte, and Quarticino, Quarte Zero, and Quarte. And I have to admit that I am involved and actually started Majorana, and I was with Ettore Fiorini, and we're now with Quarte and online and running. Okay, so this is the Majorana demonstrator is in what used to be the Home State Gold Mine, where Ray Davis did his experiments, where I did early experiments too. Out in Leeds, South Dakota, now that what used to be a gold mine has a beautiful, clean, underground laboratory built by the Department of Energy. Started, and also Mr. Sanford, who was a billionaire who just in South Dakota, who really helped the thing get started. So this Majorana demonstrator is a bunch of, it's an array of germanium detectors. I'll explain a little bit how they work, and especially work for this experiment. Surrounded in copper cryostats, surrounded by copper shields and a lead shield with some plastic around here to capture any muons that can basically get through to 4,000 meters of water equivalent, but a few do. Now, the copper was electroformed out of copper sulfate solution, so it leaves all the radioactivity behind. What a job this was. You make these things around, you want something flat, you smash it flat. You do this, it's tedious as heck. We did this in the first experiments we did with IJEX, and now it's been done to a great extent. And so everybody is dressed up like you're in a surgical situation, surgical room, an operating room. You're all clean and gloves, and the atmosphere is controlled. You're trying to get rid of all radon and thorium and uranium and everything else that gives you background, because these experiments, these half-lives are so long. You're not going to get very many counts. Okay, so these germanium detectors, the special ones that have been developed recently, they're P-type germanium with lithium on the surface, so you have a PN junction. And there's just a little tiny point here, which is a contact, and it leads to a very strange electric field configuration, which makes the electrons in the holes flow very slowly. Why? So that if you have a single site, like the double beta decay site, would just be very small region in the germanium, you would just get some smooth current like this, and if you differentiated it, you would just get a single peak from the event. But if you had a gamma rays come in, they scatter because the highest probabilities of Compton, scatter again, and finally that's absorbed by photoelectric absorption. It's liable to happen in several places. When that happens, you have bumps in the current, and when you differentiate it, you have a thing like that. You can certainly take those pulses, and if you do pulse shape discrimination, take them out. And that leads you to a very nice result. This is an example. These are gamma ray peaks, and we took out those multiple things, and it disappeared. Wait a minute, what's this guy? That's an double escape peak from a thorium peak in 2615. Double escape means that the 2.5 MeV or 2.16 MeV gamma ray came in, pair produced, and the two leptons came out, but the gamma rays got away, so it looks just like double beta decay. So the selection did not take away something that looks like double beta decay, but took away everything else. That is a fantastic tool that gets rid of a lot of background. Here's just a photograph of looking inside the clean box where people are where you have these arrays, and all of these copper pieces were made underground by precipitating things from a copper sulfate solution in electroformation. Okay, this was my job in Majorana, was to purify the germanium. This is a background situation at background spectrum at low energy. This is an ordinary germanium detector. This peak here is due to a number of things, but mainly germanium 68 that's formed by cosmogenic activity, by cosmogenic hard neutrons. Right in this room it would happen. And this comes from electron capture of cobalt 56, 57, 58 iron. Now, this was ours because we did very carefully zone refined things and kept them underground until they made the detectors. So and now we're really down below 1 keV, but I'm not allowed to show that. Why? Because somebody in the collaboration is making a paper on dark matter. And when Juan Collar sees this, Mike is going to throw rocks at me, because he couldn't do this. But even now, Super CDMS dark matter experiment is using our technique for keeping things under the ground. When you zone refine it, you take everything out, but immediately then you start getting heavy, hard neutrons. So they're going to start making the Super CDMS detectors and keeping them on the ground until, as much as they can, get rid of this tritium background. It's a tritium background. Anyway, that was a great victory. I drank half a bottle of scotch after that. Now there's another thing. This is a germanium spectrum, and if you look at just the blue, that would mean nothing's been taken out. But the rise times of alpha particles on the surface, which is 90% of our background, you take them out and you get the red, so you only get a few counts. Here was another, this is the whole spectrum, so this is Neutrinoless, two neutrino double beta decay, and up here at 2040, you'd expect to see the peak. So we've actually measured that. All right, Gerda is very similar, but they put cool their detectors, instead of in cryostats, they cool it right in liquid argon. And the liquid argon is a scintillator, so it can also reduce background. And that's happening, this experiment is being done in the Gran Sasso, and the two experiments will be joining here soon. In fact, first we'll join the data. So here's just this is all a water tank. It's a giant thing in the Gran Sasso, and this is these are the hanging germanium detectors right in the argon, being cooled by the argon, and it has to be cooled down to about 80 to 85 degrees Kelvin. That will work at 90, but then you lose a little bit of resolution. So these are just cartoons telling you how they did this. And this is if you If you use the liquid argon as a veto, then you get all of these the gray things. If you take away the argon veto events and pulse shape discrimination that I just explained, then you only get these few events in their data. So you can see the power in being able to select. What we're going to do is put 200 kilograms of these inside of in other words, we're going to do it, the Americans are going to take all of their detectors. We would have about 65 kilograms, but then the Germans have gotten new material, and we hope the Americans hope to join them with new material to have 200 kilograms and to get to 10 to the 26 or some 10 to the 27. I will show you a little graph of that. So we're going to join, but before that, we're going to join the data, try to get to 10 to the 26 years half-life. And so if we get to 10 to the 27, then we would have something in the electron neutrino, the effective mass of 30 to 60 millielectron volts. All right, this is the plan for everybody. This, of course, is the claim of Klapdor-Klein-Rothaus. We have seen it. We have neutrino-less double beta decay. I think Gerd has just about wiped that out. This is like 2.3, 10 to the 1 to 3.5, 10 to the 25 years. They were at 90% confidence level. Without our data from Majorana, they're down to 5, 10 to the 23. They're up to 5, 10 to the 23, which doesn't exclude this with a high level of confidence, but it does exclude it. Put ours in there, we probably excluded maybe 2 sigma. But more has to be done. This is another one of these things where people think they see they see the exotic thing. They're buying their tickets to Stockholm right here, but they're not going to get here that way. So what we want to do, if you have exposure for germanium in ton years, if you had 10 ton years, you could certainly get down to 10 to the 28. The whole idea is to get a ton scale germanium experiment running. You can't do just one isotope. To see an effect, you have to see it in several isotopes. Okay, another technology, one that I joined many years ago. Well, we've been doing that almost just about 20 years now. Fiorini and I just met in Russia. We decided to come bring the Americans into the Italian effort. For many, many years, the Italians, really developed this business of cryogenic detection. And it works on solid state theory. What happens is if you cool this down, we run at 8 millidegrees Kelvin. If you cool it down enough, then the specific heat goes as the temperature divided by the Debye temperature. And so the Debye temperature is the highest mode frequency of the crystal, and you can measure that. It's 232 degrees Kelvin in tellurium dioxide, and with an 8 millidegree Kelvin operating temperature, you have a factor out in front of the normal factors for the volume specific heat of 10 to the minus 14. So you have a very, very small specific heat. So when energy is applied there, you get a larger energy, a larger temperature change. And we have, this is a dilution refrigerator running at 10 to the 8 millidegrees. Then you have a piece of Teflon that sort of causes a slow cooling and slow warming of the crystal is warmed by an event inside, and then it cools off. So you get a pulse that rises and then decays slowly. Then you have a heater, which is a calibration. You can send pulses into that heater. And you put them in copper frames like this, and you build towers. And this tells how much of a change in temperature do you get for the 2527 keV energy of the double beta decay. and you just do a quick conversion here when, and this is the heat capacity that was measured for one of these big 5 by 5 by 5 centimeter crystals, and you only get like a 1.8 10 to the minus 4 Kelvin, but you can detect it. These things are built in towers. Here's one tower. Here's a person of about almost 6 feet. Here's the whole array, just before we covered it up. 750 kilos of tellurium dioxide. How big really is it? This is Paulo Gorla. He's about 3 inches taller than I am, standing next to a cartoon of it, and standing next to the real thing that's superimposed on a cartoon. This thing is now running. We did at one tower. This is the kind of energy resolution you get after you add up all of the crystals in a single tower. This was quarter zero. We published a result which is not really earth-shaking. It was combined with Corticino's 410 to the 24 years for tellurium dioxide. That's pretty good. So what do we do in the future? We have to do particle identification. So Cupid is quarter with particle identification, or it could be that. I don't know. This was proven recently to work. What we do is we detect Cherenkov light in the crystal. Cherenkov light only from electrons. Alphas on the surface, which is the killer again. We can separate the alphas from the electrons, or betas and gammas. We can separate them out then, and then we reduce a lot of the background. Now that was published very recently, the work we did in Nicaragua. Okay, so again, where would this take you? This is the same. This would be the same for the germanium experiments and for all the others. It would take you all the way through the inverted hierarchy. And even when you're doing that, you are seeing a certain amount of this is of course a log plot, you're seeing a certain amount of the normal hierarchy also. Getting down here, well, that's going to be long after my retirement. Okay, so again, we've covered a few of these things. You see so many activities, but not all of them really very far advanced. Okay, I'm just going to mention Super Nemo, which is a French experiment which is very clever. It's a bunch of sheets, and on those sheets of mylar you can deposit different isotopes. This was done in Nemo, but Nemo really wasn't aimed so much at Neutrinoless double beta decay, but it made the most beautiful spectra of 2 neutrino double beta decay ever. And so you have these sheet, and you do tracking. You can actually track these things with a tracking detector here, the trajectory and individual particle detection here. And what they're doing that's rather clever, this will be a whole bunch of these things lined up. They are doing something called BIPO, B-I for bismuth, P-O for polonium, to detect the bismuth and polonium. They take the sheets and they put them between these scintillators. And they put them between the scintillators and detect, they measure the background on the sheets before they install them in their device in France. This is in the Gran Sasso. They are in the Canfranc laboratory. There they are testing one of these elements. Clever, but okay. Then, well, we're pretty close to the end. Let me go to the end here. In Japan, they put xenon in a scintillator and put it in an unloaded scintillator, and they got an extremely nice result for Neutrinoless double beta decay. But what worries me is the energy resolution. So you're going to, this is the background they get, and then they're supposed to see something here that's rather broad. I mean, you can put a bound, but discovery is going to be difficult. And they have gotten down to here, and also the experiment of Camland Zen, 750 kilos of xenon 136 will start here very soon. And they're improving the light detection. They're hoping to improve the resolution. There's only so much you can do in a scintillator. Okay, so snow is now going to be converted to a scintillator with the xenon absorbed in it. Again, our friend Art McDonald is, he of course was the head of SNOW, and we're going to hear more about this at the TAU conference, where they are purifying the xenon, getting the other stuff out of, excuse me, the tellurium into the, not xenon, this is tellurium in tellurium 130, absorbed in a compound of tellurium into the scintillator. Again, it's going to be a problem of this kind of background and finding a few events in here. For discovery, not so good. Okay, I want to skip a few of these details. This is, of course, Giorgio Gratta's time projection chamber, which is EXO, standing for Enriched Xenon Experiment. And EXO means I can make it as big as I want. N is a number. You can make this as big as you want. This is a time projection chamber. When something happens in the liquid xenon, you can bring the charges one way with a 75 kilovolt plane here. You push the electrons this way. You can detect the light, the scintillation light that way. That's been pretty successful. That's a picture of it. NXO is make it as big as you like and put it in a big water tank in the Sudbury. Again, there's going to be a problem. The problem is one of discovery, but you can put. Why? I'm a very strong supporter of these experiments, even though I'm in the high resolution experiments. Why? If we don't see anything, these guys can put a very hard bound on it. And I think that's important. And so I've been on, people ask me all the time, you've been screaming about high resolution experiments and you're a strong supporter. Is that because you and Giorgio are friends? That too, but Giorgio and the SNOW Plus and the Japanese can put bounds that probably beyond what we can do with high resolution experiments. And I think that's important. Well, let's see, we probably get right down to the bottom. NXO claims they can get down into here. N meaning how big can you make it? But XO can certainly be down. All of them are going to be through the next generations are going to be through the inverted hierarchy. And that's what we've been told to do. Gratta says I can make it much bigger and I can get down into the normal hierarchy quite a ways. So the end goes this way. Neutrinos double beta decay is the only practical way to establish neutrinos and Majorana particles. That's important to a number of things. What's important to cosmology. If they are Majorana particles, it imply the possibility of leptogenesis. Neutrinoless double beta decay would violate lepton number. Experiments and neutrinoless double beta decay half-life sensitivity has been increasing by a factor of 2.5 times 10 cubed in a little more than 30 years, and it's about to go to another order of magnitude very soon. There are 6 or 7 experiments that are accelerating progress, and many different technologies being tried. And but I think that we're going to have some results probably in the next few years that would be satisfying to get down into the inverted hierarchy. Thanks.
Thanks to Frank, and I think that we will have time for just one question. There will be plenty of time for free discussion in the afternoon. We have moved, before we continue, I would like to say that we have slightly changed the schedule, and we have moved the talk that was scheduled for this afternoon to tomorrow afternoon. So So this afternoon will be completely free for free collaboration and discussion among participants. So time for just one question.
Mike?
So, Corey, did you say that you had 750 kilograms of
Tellurium
germanium?
oxide, not of tellurium.
Oh, sorry, tellurium oxide
Yeah, and that's
At
200
8
kilograms of
millikelvin?
tellurium-130
at 8 millikelvin?
at 8 millikelvin.
That's a big refrigerator.
It's big. Now, there are some cooler, larger masses being cooled, but not for gravitational waves detection, but they're not that cold. They don't need to be that
An 8
cold.
millikelvin is very cold.
Yes, it's damn cold.
It's
And-
almost as
and
cold
we're-
as it
and
gets
we've
here.
But Mike, we've been running that now. We've actually reached base temperature with that some time ago. We're improving things like resolution, but as far as reaching base temperature with 750, we've been down there since December.
Is that a custom made?
Pardon?
Is that a custom made dilution refrigerator?
No, it's, it was made, yeah, excuse me, it is custom made.
Yeah.
It's made in Holland.
Who's responsible for that?
Pardon?
Who's responsible for that design? Who's behind it?
Frosati, Giorgio Frosati, who's in Holland. He used to be a collaborator, but now he can't be because we had to pay him millions of dollars for the.
There was one question from Jose, I think.
Well, it was just, if you could zoom in again, your conclusions concerning discovery versus constraining amongst the leading experiments in the future, like Legend, Nexo, and the bolometer. In other words, you were saying that you may constrain the transdorolometer decay all the way to the bottom of the inverted
Right.
hierarchy. But which experiment do you think would actually have the chance of observing it?
Well, I think you have to get you have to have the good resolution and almost no background.
And so the candidates left for that?
Well, Quarry has still a background problem. And of course, one of the problems with the germanium experiments is they're so expensive to go to a ton. We paid $100,000 per kilo. I know this because I was involved in it. $100,000 per kilo of germanium 76 at 87%. Then you have to make detectors. We got a 70% yield, and I think I could do better. But you're talking about millions of dollars. You're talking $100 million to build just the isotope. So it's expensive.